Welcome to the Robert Judat podcast, where intelligence sharpens in the dark. Research-driven, LLM-forged, human-verified. Stay curious.
Right now, as you're listening to this, some of those powerful technology companies in human history are actively buying up decommissioned nuclear power plants.
Yeah,
Yeah.
literally buying nuclear plants.
Right. Not investing in green energy startups, not building solar farms. I mean, they are literally trying to resurrect 1970s era nuclear reactors just to keep their computers turned on.
Just wild when you really think about it.
It's completely nuts. So whenever I turn on the news or talk to people about the future of artificial intelligence, and I hear that phrase repeated over and over, the chip shortage, it honestly drives me crazy.
Oh, I bet. It's everywhere.
It's always framed as this simple manufacturing hiccup, right? Like a car factory that temporarily ran out of steering wheels, and as soon as they stamp out a few more pieces of silicon, this whole AI revolution will just seamlessly pick up right where it left off.
Yeah, it's a very comforting narrative because it implies a nice linear problem with a perfectly linear solution.
Right. Just build more factories.
Exactly. We just build a few more fabrication plants, we print a few more logic dates, and presto, the algorithms just keep getting smarter. But that narrative is completely, it's fundamentally broken.
Broken on multiple levels.
Right. The people repeating it are fundamentally misunderstanding the physics, the economics, and honestly, the physical architecture of what is actually being built today. We aren't just building computers anymore.
And that is exactly why you are here with us for this deep dive. Because our mission today, for you listening, is to completely dismantle that mainstream myth.
Yeah, it needs to go.
It really does. Because the truth is, AI progress isn't bottlenecked by a simple lack of silicon chips. We've crossed an irreversible threshold here. The paradigm is completely shifted. We're no longer talking about data centers as these massive warehouses filled with thousands of independent, disconnected servers.
Right. Running separate little tasks for different customers. The era of standard cloud computing, where you have a million independent microservices running asynchronously in the background, that era is effectively over when we talk about artificial intelligence at the frontier.
Okay, let's unpack this, because to truly grasp what is happening here, you have to look at the physical, macro-level scale of what is being constructed right now. And you know me, I spend my time looking at the concrete, the steel, the supply chains, the massive thermodynamic footprint of these facilities.
For deck review, yeah.
Right. I'm looking at the fact that these new AI data centers are pulling gigawatts of power. We are building structures that consume as much electricity as small European nations, all to power what is functionally a single massive continuous entity. We're building monolithic supercomputers. Is one brain filling a 1 million square foot warehouse?
Which is just what's fascinating here is that the very definition of the word computer has totally mutated.
Yeah.
If you went back 10 years, a computer was a single processor slapped onto a motherboard.
Right.
Today, the computer is the entire building. It's a synchronized warehouse of silicon acting as one giant continuous brain. But to understand why the building itself is a computer and why that building is currently struggling so hard to scale up, we actually have to zoom all the way in.
All the way to the micro level.
Right. Before we can talk about the gigawatts of power and the concrete, we have to talk about the nanometers. We have to look at the microscopic realities of semiconductor physics, because the real choke point right now, it isn't actually printing the silicon.
It's not.
No, it's the agonizingly complex process of stitching all those tiny pieces together.
Okay, so let's get into that, because this brings us to the first major bottleneck that I think the broader public completely misunderstands. The so-called chip shortage is actually an advanced semiconductor packaging shortage, isn't it?
Yes, exactly.
Because for decades, the industry just relied on Moore's law. We just made the transistors smaller and packed more of them onto a single, flat, monolithic die. But we've hit a physical wall now. We literally can't just make the chip bigger anymore.
Yeah, we hit what's called the photolithographic reticle limit.
The reticle limit. Okay, explain that.
Right. It sounds like dense jargon, but it's actually a fundamental physical law of the optics used in manufacturing. To make an advanced AI chip today, companies use extreme ultraviolet or EUV lithography machines.
These are the ones built by ASML, right? The machine's the size of a city bus.
Exactly. City bus-sized machines. Basically, you are using incredibly short wavelength light to print microscopic transistor patterns onto a raw silicon wafer. But the EUV tool, the internal optics, and the mirrors, they can only print a pattern up to a specific maximum physical area in a single exposure.
Oh.
And that maximum area is the reticle limit. The light just can't physically bend wide enough to print a larger surface area with that level of precision.
So if I'm understanding this right, we literally cannot manufacture a single piece of silicon large enough to hold all the logic gates required for a massive trillion-parameter AI model, because the camera lens of the manufacturing machine just isn't wide enough to snap the picture in one go.
That is a great way to look at it. The AI models are demanding an absolutely massive amount of logic surface area. We can't just print one giant chip. So the engineers had to pivot. They adopted a process called heterogeneous integration.
Okay, heterogeneous integration.
Right. They take what would have been one giant, impossible to print chip, and they fracture it into smaller individual pieces called chiplets.
Chiplets. But I mean, once you break it into a bunch of separate chiplets, you have to put Humpty Dumpty back together again.
Exactly. You have to connect them.
Which brings us to arguably the most important company on Earth right now, Taiwan Semiconductor Manufacturing Company, or TSMC, and specifically the acronym that is functionally dictating the pace of global AI progress right now, CoWoS.
Oh, yeah. CoWoS, chip on wafer on substrates. This is the absolute bleeding edge of advanced packaging. Once you have all those smaller fractured logic chiplets, you have to place them onto a shared silicon basement called an interposer.
So it's like a foundation.
Right, exactly. But here's the catch. It isn't just the logic units. To do AI math, those logic units need data, and they need it instantly. So CoWoS meticulously bonds those central logic units directly adjacent to high bandwidth memory modules on that same silicon interposer.
Wow, okay.
And the microscopic wiring, the physical trace lines between the logic and the memory, it has to be flawlessly aligned to achieve the massive data transfer rates required.
So think of standard chip manufacturing like printing a highly detailed map. The reticle limit means our printer paper is suddenly just too small for the massive map we need to print.
Yeah, good analogy.
So CoWoS is like meticulously taping multiple sheets of paper together side by side without breaking a single microscopic road that crosses the seam between the pages.
Precisely. And if even one of those microscopic roads is misaligned by a fraction of a human hair, the entire multi-thousand-dollar processor goes straight in the trash.
That is insane.
It is. And because that alignment process is so insanely difficult, CoWoS is the ultimate bottleneck. Even if TSMC flawlessly fabricates millions of logic dies at their cutting-edge 2-nanometer or 3-nanometer nodes, they can't ship them as functional AI accelerators like the NVIDIA Blackwell or the AMD MI300.
Without running them through that CoWoS packaging line.
Exactly.
And from a macro perspective, the demand is just drowning the supply. I mean, looking at the sources, the demand-to-supply ratio for CoWoS is sitting at 1.4 to 1.6. TSMC executives are publicly stating that this advanced packaging capacity is structurally sold out through 2025 and entirely into 2026.
Yeah, they literally cannot build it fast enough.
Every tech giant in the world is standing in a line that is barely moving. But I'm looking at the capital expenditure numbers, and it's causing a massive ripple effect upstream, isn't it?
It creates a catastrophic cascading problem up the entire supply chain, specifically for companies like ASML who build those bus-sized EUV lithography machines. Because we are fracturing these chips and packaging them together into larger and larger unified systems, the sheer volume of raw silicon required is escalating dramatically.
Volume is just exploding.
Right. This is what the industry calls the wafer math.
Okay, let's talk about the wafer math, because the financial scale here is staggering. If you look at current generation AI architectures like the NVIDIA Blackwell systems rolling out now, it takes about 2.5 raw silicon wafers to yield a single functional system unit.
Yep, 2.5.
But when you look at the industry roadmaps for the 2027 architectures, like the anticipated Rubin product line, the projection is that it will demand up to 10 wafers per system.
10 wafers per system.
That is a 400% increase in raw wafer demand just to achieve an equivalent system output.
It is an absolute explosion in the sheer physical volume of silicon that has to be processed, exposed, etched, and packaged.
I mean, how does a highly specialized supply chain even begin to absorb a 400% increase in raw material demand over a 2 to 3 year period?
With immense difficulty, a lot of brute force, and massive, massive capital expenditure. I mean, ASML is trying to accelerate this on their end. They have increased the productivity of their latest NXT.3800 EUV tools by over 40%, pushing the throughput to 220 wafers per hour.
Okay, that's significant.
It is, but there's a massive execution risk looming, because the next leap in lithography is high-NA EUV, which uses high numerical aperture lenses to print even smaller features.
Right.
But here's the irony: high-NA actually halves the field size, which complicates that reticle limit we just talked about even further.
Wait, it cuts it in half?
Yes. You can print smaller transistors, but your camera lens gets even narrower, and high-NA isn't expected to hit high-volume manufacturing until 2028 or 2029 anyway.
Oh, wow. So we have this massive gap. We have an exploding demand for silicon surface area, brutal packaging choke point, and the next generation printing tools are still years away. This explains the sheer panic in the capital reallocation we are seeing. TSMC is forecasting an incredible $52 to $56 billion in CapEx for 2026 alone. But the crazy part is that 10 to 20% of that, up to $10.8 billion in a single year, is being explicitly diverted away from traditional logic nodes and shoved directly into advanced packaging, testing, and mask making.
They are basically triaging their entire business to widen the narrowest part of the funnel.
Right.
But even with $10 billion, TSMC physically cannot build CoWoS facilities fast enough. The overflow is massive. They are literally having to outsource their own advanced packaging to what are called OSAT providers.
OSAT?
Yeah, outsourced semiconductor assembly and test companies.
Like Amkor, right, because
Yeah.
the data shows Amkor is catching a massive wave of TSMC's overflow, estimated at roughly 180,000 to 190,000 CoWoS equivalent wafers annually.
Exactly. Amkor is reacting by tripling its own capex to around $2.5 to $3 billion in 2026, and they're dedicating up to 70% of that just to build a gigantic new advanced packaging campus in Arizona. They are scaling their own high-density fan-out platform just to catch the spillover from TSMC.
It's just wild, and you can see how strategically critical this packaging layer has become by looking at the broader competitive landscape, right?
Yeah.
Because Intel, for example, is desperately trying to position its own proprietary packaging technology called EMIB as a viable alternative to TSMC's CoWoS.
Oh, yeah. They are trying hard. They are trying to lure desperate customers by saying, hey, we don't have the CoWoS backlog. Come build your chips with us.
Right.
But integrating this stuff is brutally hard. Intel actually suffered a $2.5 billion operating loss in its foundry segment recently, largely due to internal scaling challenges and broader supply deficits as they try to compete in this highly sensitive advanced packaging arena.
It's basically a high-stakes, multi-billion-dollar game of microscopic Tetris.
Microscopic Tetris, yeah, that's exactly what it is.
But the logic chiplets are only half of the equation sitting on that CoWoS interposer. The other half is the memory. And this introduces a whole separate, equally terrifying crisis. So let's talk about the memory wall and the transition to HBM, or high bandwidth memory.
Right, because standard memory arrays, like the DRAM sitting in the laptop on your desk, they are perfectly fine for general computing tasks. But an AI logic unit is so incredibly fast and requires so much data simultaneously to do its matrix math that standard DRAM just cannot feed it fast enough.
The processor just ends up waiting.
Exactly. The logic unit ends up sitting idle, starved for data. That is the literal definition of the memory wall. To solve this, the industry created HBM. Instead of laying memory chips flat next to each other on a board, HBM stacks them vertically, like a skyscraper of memory.
Hold on, you're telling me they are stacking microscopic sheets of silicon on top of each other? How do the floors of that skyscraper even talk to each other?
Through an incredibly delicate technology called through-silicon vias, or TSVs. Yeah. They literally drill microscopic holes vertically down through the entire stack of silicon memory dies, and then they fill those holes with conductive metals so the data can travel straight up and down the skyscraper.
That sounds like an absolute manufacturing nightmare. I mean, drilling holes in silicon at the microscopic level, the failure rates must be astronomical.
It is arguably the single tightest, most sensitive component in the entire AI material stack. Stacking 12 or 16 of these delicate memory dies vertically requires hybrid bonding and microbump processes that demand extraordinarily tight process controls.
Because if it's off by even a little bit,
If even one microbump fails to connect perfectly, the whole 16-story skyscraper is dead. The whole thing.
wow.
And this is all coming to a head right now because the industry is about to undergo a massive architectural shift to the new HBM4 standard, slated for mass production between late 2025 and 2026.
And reading these specs, HBM4 is just an incremental speed boost. It's a total redesign of how memory functions.
It is a radical shift. HBM4 actually integrates a custom logic die directly into the base of the memory stack. It effectively turns the memory module itself into a localized POE processor that can handle minor operations on its own without having to bother the main GPU.
That's fascinating.
And it also doubles the physical interface with 22048 bits per stack.
And they are using PAM4 signaling to hit those massive data speeds, right?
Yeah.
Reaching over 2.0 terabytes per second per stack.
Yes, PAM4 or pulse amplitude modulation 4 level. Instead of standard binary signaling, which is just ones and fours, on or off PAM4 allows them to send 4 distinct voltage levels per signal, which basically doubles the data rate.
Right.
But pushing 4 delicate voltage levels through a 16-high vertical stack of silicon requires almost magical precision, which is why the current market dynamics between the memory suppliers are so wild to watch.
It really is shaping up to be a massive clash of architectures.
Yeah.
Because on one side, you have the reigning champion, SK Hynix. They currently hold about 50% of the HBM market share, and their capacity is completely sold out through 2026.
Yeah, and SK Hynix achieved that dominance through extreme manufacturing reliability. They stuck with a proven process called mass reflow molded underfill, or MRMUF, for their die stacking.
MRMUF, I've read about this. It basically means they are using highly optimized, proven techniques to sort of glue and bake these layers together, right?
In simple terms, yes. And crucially, they are managing the immense heat generated by these vertical stacks using wafer-level passive heat spreaders that are perfectly matched to the thermal expansion coefficient of the silicon itself.
Because when silicon gets hot, it expands.
Exactly. And if the glue expands at a different rate than the silicon, the skyscraper tears itself apart.
Okay.
But SK Hynix solved that. It is reliable, it yields well, and it is why they own the market right now.
But then you have the challenger, Micron. They only hold an estimated 10 to 21% of the market right now, but their strategy is incredibly aggressive. The data notes that between 2018 and 2026, Micron filed 621 HBM-related patents. That is nearly double the 315 patents filed by SK Hynix in the same period.
They are going all in.
Yeah, Micron is betting that the only way to win the HBM4 era is to just leapfrog the incumbent with radical, highly complex new physics.
And they really are. Micron is proposing active hybrid bonding and advanced polymer encapsulation to build their 12-high and 16-high stacks. But the most radical difference is their approach to thermal management. While SK Hynix relies on those passive heat spreaders, Micron is actually patenting through silicon trench cooling.
Wait, trench cooling, like inside the memory chip?
Yes, inside the chip. They want to actively circulate cooling fluid and dielectrics directly through the microscopic trenches of the vertical silicon stack itself.
That is just, I have to play devil's advocate here for a second.
Go for it.
From a macro capital allocation perspective, if memory yields are so incredibly sensitive and packing this much heat and density into a CoWoS package is this difficult, why not just bypass this entirely?
What do you mean?
Well, if standard GPUs are so bottlenecked by HBM and TSMC's packaging, why doesn't the industry just invent a different kind of processor architecture that doesn't need to be built this way?
That is exactly what a significant portion of the industry is attempting to do right now. They are trying to escape the packaging trap by building specialized ASICs application-specific integrated circuits.
Right.
But to understand why these alternative chips work and why they haven't entirely replaced standard GPUs yet, we have to split artificial intelligence into its 2 core workloads, training and inference.
This is a crucial distinction. Training is the process of building the AI's brain, right? You feed it petabytes of data, it updates trillions of neural network weights, and it slowly learns how to understand patterns. It is incredibly compute intensive.
And inference is what happens when you, the listener, actually ask the AI a question on your phone. You prompt ChatGPT and it infers the answer based on its training.
Right.
But even inference itself is broken down into 2 very distinct computational phases with completely different hardware requirements.
Okay, the first phase is the prefill, or prompt processing.
Yes. When you type in a prompt, or you upload a PDF, the hardware has to read and process that entire block of text. This phase is natively parallel. It is computationally intensive, but it requires relatively moderate memory bandwidth, so standard processors are pretty good at this.
But the second phase is decode. This is output generation, where the AI is actually spitting out the answer.
And decode is inherently serial. It generates 1 token, 1 word at a time. It is computationally very light, but it is extraordinarily memory bandwidth intensive.
Why is that?
Because to generate every single word, the hardware has to fetch the entire neural network model from memory. every single time, word by word.
Oh, wow. Okay, so using a traditional massive NVIDIA GPU to do both the prefill and the decode is incredibly inefficient.
Highly inefficient. During the decode phase, the massive compute cores on the GPU are mostly sitting idle, just waiting for the HBM memory to serve up the data. To resolve this, major cloud providers are moving towards something called inference disaggregation.
Meaning they split the tasks.
Exactly. They are physically separating the two workloads onto entirely different specialized chips.
And the sources highlight Amazon Web Services doing exactly this. AWS has partnered with Cerebras. They use their own proprietary AWS Trainium 3 ASICs to handle the compute-heavy prefill phase. Then, they route the memory-heavy decode phase over to Cerebras CS3 systems.
And the Cerebras CS3 is a masterpiece of alternative engineering. We talked earlier about how the reticle limit forces us to fracture silicon into chiplets and tape them back together on a CoWoS interposer, right?
Yeah.
Cerebras looked at that problem and said, what if we just don't cut the wafer?
Right. The Wafer Scale Engine 3, or WSE3, they literally leave the entire 300mm silicon wafer completely intact. It was a single dinner plate-sized chip with 4 trillion transistors. It has 56 times the surface area of a standard GPU.
It's massive, and by leaving the wafer uncut, they completely circumvent the traditional CoWoS packaging bottlenecks.
Yeah.
The microscopic communication pathways remain fully integrated across the entire silicon expanse.
That means
This yields immense memory bandwidth, allowing the Cerebras system to execute those memory-hungry decode phases without hitting the standard memory wall that plagues traditional GPUs.
And it isn't just Cerebras doing this. Look at Grok. They have taken a different but equally radical approach with their language processing units, or LPUs. Grok decided to abandon the entire HBM memory hierarchy completely. They don't use it. Instead, they rely on massive arrays of on-chip SRAM.
SRAM, or static random access memory, is incredibly fast. It's the memory usually placed right next to a CPU core, but it is traditionally very low density and highly expensive.
Right.
But by loading up their chips with massive amounts of SRAM, Grok achieves ultra-low deterministic latency. They execute inference operations up to 18 times faster than standard GPUs for specific workloads because the data never has to leave the processor die to reach a separate memory stack like HBM.
So you have these incredible alternatives. Cerebras bypassing packaging by keeping the whole wafer, Grok abandoning HBM for pure SRAM speed, and you also have Google's TPUs, Intel's Gaudi architectures.
Lots of options.
But here is the massive red flag for me as a strategist. If enterprise IT departments deploy these proprietary ASICs, aren't they just trading a supply chain bottleneck for a massive vendor lock-in risk?
If we connect this to the bigger picture, that is the exact reason why specialized ASICs haven't taken over completely. ASICs are incredibly powerful, but they are incredibly rigid.
Because a Grok LPU is absolutely amazing at inference, but it cannot perform model training.
Right. And a Cerebras wafer requires entirely bespoke, custom-built power and cooling infrastructure. You cannot just slide a dinner plate-sized chip into a standard Dell server rack.
And there's the longevity risk, too. The sources point out the impending discontinuation of certain ASIC lines, like Intel's Gaudi 3, which is already slated to sunset around 2026 or 2027.
Yeah, it's soon.
If you're an enterprise IT director, dropping $50 million on a multi-year deployment of proprietary chips that might not even be supported in 3 years is a terrifying prospect.
Which is precisely why standard, highly flexible GPUs still maintain an 80% market share. Yes, they're brutally bottlenecked by CoWoS packaging and HBM yields, but they are flexible. A GPU can train a model on Monday, run inference on Tuesday, and render 3D graphics on Wednesday. They can handle the entire pipeline.
Okay, so whether you are using a standard GPU or a specialized ASIC, the processor still has to retrieve the foundational data from somewhere. It has to pull it from long-term storage. And this brings us to one of the most unexpected macro-level bottlenecks in the entire system: the storage wall.
Oh yeah, the storage wall. It is so easy to obsess over the speed of the processors and the memory, but the underlying data storage fabric dictates the scale, the persistence, and the recall speed of everything the AI does.
Especially now with RAG.
Yeah, exactly. This is especially critical now as AI transitions from just generating text based on its initial training to using retrieval augmented generation, or RAG. This involves massive multi-agent systems where the AI has to constantly search through vast corporate databases to find new information in real time.
And for the longest time, hyperscale data centers just relied on hard disk drives, or HDDs, good old spinning magnetic platters. They were cheap and their storage capacity scaled massively, pushing beyond 20 terabytes and toward 30 terabytes per drive. But there is a fatal flaw when it comes to AI.
The physical mechanics of the drive didn't get any faster.
Right.
The density increased, meaning they packed more data onto the same spinning platter, but the electromechanical read-write head, the actual physical needle that reads the magnetic data, it cannot spin any faster without physically tearing itself apart.
So it's a bottleneck.
Yes. Consequently, the input-output bandwidth per terabyte, the speed at which you can retrieve a specific piece of data relative to the size of the drive, has consistently declined.
So you have this absurd scenario where a $30,000 GPU is sitting there burning immense power, fully ready to process data, but it's forced to sit idle and wait for a mechanical needle to physically spin across a magnetic disk just to fetch a text file.
Yeah, it is a severe latency crisis. If an AI cluster is waiting for a mechanical disk, it utterly destroys the economic viability of that multi-million-dollar rack.
Because it's just sitting there.
Exactly. AI inference is fundamentally a data retrieval story. If the retrieval is slow, the AI is slow. And to compound the issue, the explosion in AI demand has caused severe disruptions in the hard drive supply chain itself.
Really?
Yeah. Manufacturers are trying to transition to heat-assisted magnetic recording, or HAR, to increase densities further, but they are hitting major production friction. Lead times for massive HDD orders are now stretching over a year, and their traditional cost advantage is eroding fast.
Which is driving a massive industry pivot toward quad-level cell, or QLC, and solid-state drives.
Yep, SSDs.
QLC is fascinating because it sits right in the sweet spot. It is cheaper and denser than high-speed TLC flash, but infinitely faster than a spinning hard drive. And the capacities they are hitting are mind-bending. The sources mention Micron unveiling the 6600 Ionic QLC drive, hitting 122 terabytes in a single standard-sized drive, with roadmaps heading to 245 terabytes.
Which means you can functionally replace 3 high-capacity, space-consuming hard drives with a single 122 terabyte QLC SSD and get dramatically superior throughput and lower latency.
Right.
But the most critical factor driving QLC adoption in these AI data centers isn't just the speed, it is the energy efficiency.
Because in a modern AI facility, power is the single most precious commodity on Earth.
Absolutely. The research demonstrates that high-capacity QLC SSDs are up to 79.5% more power efficient than hybrid setups using HDDs and TLC cache. When you scale your storage environment to petabytes or exabytes, that energy efficiency translates directly into massive operational leverage.
The numbers in the report are striking. Because of the power savings on the storage tier, data center engineers can deploy up to 26.3% more computational infrastructure, more GPUs, within the exact same facility power envelope, simply by swapping out the spinning disks for QLC flash.
It's a huge gain.
Look at the power draw comparisons. At a 10 petabyte scale, a TLC SSD setup draws over 4,000 watts. The equivalent QLC setup draws just 3,230 watts. That is nearly a 20% efficiency gain just on the solid-state transition, let alone replacing mechanical drives.
And it isn't just the physical storage hardware that is adapting. The software layer that interacts with this storage is undergoing a structural revolution, specifically regarding vector databases.
I want to spend a minute here because an AI doesn't search for information like a human does. It doesn't look for keywords. It uses semantic similarity.
Right.
It turns sentences and concepts into massive mathematical vectors, often with 1,000 dimensions, and then searches a vector database to find points that are mathematically close to each other.
And executing an approximate nearest neighbor search across billions of high-dimensional vectors using standard CPUs creates an untenable processing latency. The CPU simply cannot do the math fast enough.
So what's the fix?
Storage architectures are increasingly integrating GPU acceleration directly into the data retrieval layer itself.
The storage servers themselves are getting GPUs.
Yes. Companies like VS Data are building things like the CNode X server. It combines their proprietary AI operating system with onboard NVIDIA Blackwell GPUs, whose sole job is to accelerate data vectorization and search before it even hits the main compute cluster.
Ah, so offloading the work.
Exactly. They are utilizing open source libraries like NVIDIA QVS to explicitly offload the vector indexing processes from the CPUs to the GPUs. And the hardware acceleration yields extraordinary results.
Let me give you the exact metric from the Kioxia test cited in the sources because it perfectly illustrates why this is necessary.
Oh, for it.
They ran a billion-scale test, indexing 1,024 dimensional vectors. When they ran that process on highly optimized standard CPUs, it took 28.4 days to build the index. nearly a month.
A month.
But when they shifted to GPU-accelerated storage using 4 NVIDIA Hopper GPUs in the QVS library, it took just 1.4 days.
That is a factor of 20 reduction in time. This hybrid integration of massive QLC storage densities combined with localized GPU-accelerated retrieval effectively shatters the AI data storage bottleneck.
It really does.
It makes multi-billion scale vector search not just theoretically possible, but economically and temporally viable for enterprise deployments.
Okay, so we have the chips, we have the advanced packaging, and we have the high-density storage. But whether you are using a single massive Cerebras wafer or 1,000 NVIDIA GPUs fed by high-density QLC drives, all of these components have to talk to each other.
Right, the network.
In an AI training run, they don't act as independent servers. They must act as a single flawless organism. And that brings us to the connective tissue of the supercomputer, the network fabric.
When we talk about AI training models with trillions of parameters, the concept of a single computer has truly expanded to encompass the entire data center hall. The true structural boundary of AI computation is no longer the silicon die. It is the network interconnect that binds hundreds of thousands of GPUs together.
And the requirements for this network are unforgiving. AI training relies on highly synchronous collective operations, specifically something called the all-reduce function.
Right. In an all-reduce operation, every single GPU in the cluster must broadcast its mathematical gradient updates across the network, and every single GPU must await the responses from all the others before it can proceed to the next training step.
It has to wait for everyone.
Exactly. It is a massive synchronized heartbeat. Imagine an orchestra with 100,000 musicians. If one musician misses a beat, the entire orchestra stops playing until they catch up.
And what happens if the network stumbles?
Yeah.
If one musician drops their sheet music?
If the network drops even a single packet of data due to congestion, the resulting TCP retransmit or RDMA retransmit causes a microscopic delay, perhaps 10 to 100 milliseconds.
Which sounds tiny.
It sounds tiny. But in a cluster of 100,000 GPUs, that delay cascades. The entire cluster pauses to wait for that dropped packet. Over a multi-month training run, those cascading pauses result in millions of dollars in lost compute utilization. The GPUs are burning maximum power, doing absolutely nothing, just waiting on the network.
Which means the network fabric must be absolutely lossless. Zero dropped packets. And this strict requirement has sparked a brutal architectural war between two distinct networking philosophies: InfiniBand versus RosaVid 2.
InfiniBand is the incumbent. It is a purpose-built standard designed specifically for high-performance computing, and its superpower is its native credit-based flow control mechanism.
Here's where it gets really interesting. Think of InfiniBand like a VIP reserved lane on a highway, where you literally cannot enter the on-ramp unless the parking attendant at your destination has guaranteed you an open parking spot.
Right.
The sender is physically barred from transmitting a packet of data unless it has explicitly received buffer credits from the receiving switch.
Because of that strict credit system, InfiniBand guarantees zero packet drops due to buffer overruns. It operates with an incredibly stable, highly deterministic tail latency of just 1 to 2 microseconds. In ideal conditions, it drops to 0.5 microseconds. It bypasses the standard software protocol stack entirely, making it the lowest latency commercial network available. It is mathematically perfect for tightly synchronized AI training.
But InfiniBand is proprietary. It is expensive, and it limits you to highly specialized hardware. That is why the major hyperscalers, the Googles, the Metas, the Microsofts, are fighting tooth and nail to make RoSev 2 work. RoSev 2 stands for RDMA over Converged Ethernet.
They want to bring the massive economic scale and diverse supply chain of commodity Ethernet into the AI space. They don't want to be locked into one vendor.
But Ethernet is fundamentally a best-effort lossy protocol. It was designed to drop packets if the network gets congested and just ask the sender to resend them later.
That is fine for loading a web page or sending an email, but it is catastrophic for an AI all-reduce operation. So to use Ethernet, they have to aggressively engineer it to mimic InfiniBand's lossless nature. They rely on two highly complex mechanisms.
First is priority flow control, or PFC. Going back to our traffic analogy, if InfiniBand is the VIP lane with guaranteed parking, PFC is a system of aggressive red lights. It is a hardware-level mechanism that sends physical pause signals back upstream when a network switch buffer starts getting full, creating a hard physical back pressure to stop traffic.
And the second mechanism is explicit congestion notification, or ECN. This is more like a radio warning system. It is a software-level flag embedded in the packet header that warns the receiving network interface card that congestion is building up. prompting the sender to dynamically throttle its transmission rate before a pileup occurs.
But the tuning required to make PFC and ECN work perfectly together across 100,000 GPUs is maddening.
It is so hard.
If you tune it poorly, ROSA V2 networks suffer from severe instabilities. The sources detail that if you rely too heavily on PFC without ECN, you get head-of-line blocking cascades. The pause frames propagate backward through the network, paralyzing entire switch fabrics like a traffic jam backing up for miles across the city.
Yeah, total gridlock.
But if you rely on ECN without PFC, you end up dropping packets during sudden traffic spikes.
It is a massive, delicate balancing act, and even when tuned perfectly, ROSA V2 has slightly higher base latencies of 2 to 5 microseconds due to the Ethernet encapsulation overhead. But despite these challenges, hyperscalers are converging on ROSA V2 because avoiding single-vendor lock-in and riding the massive wave of Ethernet innovation is just too economically vital.
Okay, but whether you are pushing data over InfiniBand or ROSA V2, the physical medium transporting those signals is crashing into a hard physical limit. We are talking about the physical wiring itself. High-speed electrical serializer, deserializer, or SERDES, components are used to drive signals over traditional copper wiring.
And copper is failing us at these speeds.
It is.
As bandwidth scales up to meet AI demands, pushing electrical signals through copper traces results in severe signal degradation. More importantly, it requires immense power draw to push the signal through the physical resistance of the metal.
Moving electrons through copper generates resistive heat, joule heating.
Exactly. We are hitting what the industry calls the silicon wall. To bypass this, the entire data center architecture is orchestrating a fundamental shift from copper to optical signaling. We are replacing electrons with photons.
Which is incredible.
It is, and this transition is moving the optical interfaces progressively closer to the compute logic itself.
This is co-packaged optics, or CPO, right?
Yes. We are bringing the optical transceivers directly onto the switch substrate. Instead of having a long, power-hungry copper trace running across a motherboard to a pluggable module on the front panel, the parallel optical fibers plug directly into the silicon package itself.
Meta has been leading the charge on this, recently completing a massive 90 million-hour reliability test for CPO infrastructure. They're proving it can survive in a real-world environment and paving the way for commercial maturity around 2028.
And you also have the Open Compute Interconnect, or OCI, multi-source agreement, backed by industry heavyweights, establishing standards for deep in-package optical links.
And the justification for OCI and CPO isn't just about reaching further distances. By completely removing the electrical overhead of those power-hungry SERDES components, optical interconnects are crossing a new threshold. They are fundamentally more energy efficient per bit than copper over any distance, even within the same rack.
Which explains why NVIDIA is going on a massive $6.5 billion investment spree into optical component makers like Coherent, Lumentum, and Marvell. Securing an optical supply chain capable of matching AI scale is now a strategic imperative.
But here is where it goes from an engineering evolution to pure science fiction.
Oh, this is my favorite part.
The utilization of photonics of light is no longer just limited to moving data across the network.
Right.
It is now actively subsuming the actual computation layer. We are talking about optical computing.
Yes. Traditional electronic AI accelerators are facing that silicon wall. At near-atomic transistor scales, Moore's law fails due to quantum tunneling, leakage currents, and heat dissipation. So companies like Lightmatter have taken optical computing out of the theoretical laboratory and put it into production-ready silicon, specifically a processor architecture known as NVICE.
I need you to slow down here and explain this. How does a processor compute using light instead of electricity?
The physics of it is incredibly elegant. In a traditional electronic processor, math is done by physically switching billions of transistors on and off.
Right.
In the NVICE optical processor, there are no switching transistors doing the core math. Instead, lasers are fed into complex networks of microscopic optical components, primarily things called Mach-Zehnder interferometers, or MZMs.
Mach-Zehnder interferometers. And how do MZMs do math?
Through the natural physical phenomenon of wave interference.
Wave interference.
Think of it like dropping two pebbles into a perfectly still pond. When the ripples meet, they either combine to make a bigger wave, or they cancel each other out and the water goes flat.
Oh, okay. I can picture that.
When coherent light passes through these interferometers in the silicon, the light waves interact in the same way. Depending on how they are tuned, the light waves either amplify each other or cancel each other out. That physical wave interference implicitly calculates linear transformations. Specifically, the massive matrix vector multiplications that underpin all deep learning models. The brightness of the output light is the answer to the multiplication.
That is insane. It is literally doing math at the speed of light.
Yes, and with profound physical advantages. Photons have zero mass. They do not interact or interfere with one another when crossing paths, unlike electrons. And crucially, they do not suffer from Joule heating. There is no electrical resistance because there are no moving electrons doing the math.
The processor operates without the thermal constraints of standard silicon, and the performance metrics validated across models like ResNet, BERT, and NanoGPT are staggering. We are talking about an unprecedented energy efficiency metric of 262 trillion operations per watt, or TOPSW, and an ultra-low latency of just 200 picoseconds per matrix vector product. It is a radical paradigm shift for the post-transistor era.
But until those optical computers fully take over the industry, we are stuck with the electronic processors of today.
Right. The reality we live in now.
And the problem with all these incredible advancements we've discussed, the massive CoWoS packages, the 4 trillion transistor wafers, the high-density QLC drives, the tightly packed network switches, is that they consume and generate an apocalyptic amount of energy and heat in a highly concentrated physical space.
Which brings us to my absolute favorite topic, thermodynamics and the physical reality of the data center building itself. We have established that the monolithic supercomputer is incredibly powerful, but it is also about to melt the building it sits in.
The consolidation of all this compute power into massive, heterogeneous architectures has triggered a severe crisis in physical facility infrastructure. The legacy data centers that were built over the last 20 years were engineered for general cloud workloads. They were absolutely never engineered to support the thermodynamic realities of modern AI.
Let's talk about the 100 kilowatt inflection point. For the past decade, a typical enterprise IT rack, the physical metal cabinet holding the servers, maintained an average power density of roughly 5 to 15 kilowatts. But modern AI accelerators, where individual GPUs frequently exceed a 1,000-watt thermal design power all on their own, have completely shattered those standards.
A current generation AI training cluster demands 40 to 60 kilowatts per rack, and the cutting-edge platforms like the liquid-cooled NVIDIA GB200 NVL72 demand up to 132 kilowatts in a single enclosure.
And that is just today. The industry roadmaps for the next generation platforms, the Blackwell Ultras and the Rubin servers, are projecting staggering power densities. They are expecting loads to reach 250 kilowatts and 900 kilowatts per individual rack by 2027.
Almost a megawatt.
That is approaching 1 megawatt of power in a footprint the size of a large kitchen refrigerator.
This exponential increase in power density radically alters the fundamental economics and physical engineering of the entire building.
I mean, looking at the macro cost, it's unbelievable. The hardware cost of an average AI rack has surged sevenfold, escalating from roughly $500,000 for standard enterprise gear to an astonishing $3.9 million for a fully loaded AI rack.
$3.9 million.
And building a greenfield facility, a brand new data center from scratch, capable of supporting these 100 kilowatt loads, incurs infrastructure costs of $200,000 to $300,000 per rack space before you even buy the servers to put in them.
Even retrofitting a legacy facility for a moderate 40 kilowatt density costs up to $100,000 per rack in infrastructure upgrades.
I have to ask, at what point does the physical building, the power delivery, and the cooling systems cost more than the multi-million-dollar chip sitting inside them?
We're getting there. The structural and electrical modifications required are immense. Take the electrical delivery. Standard alternating current, or AC, incurs excessive energy loss when you try to deliver it at these extreme densities. So, high-density designs now utilize a 400-volt to 800-volt direct current, or DC, busbar system.
DC power.
Right. They rectify the AC to DC much closer to the source, sometimes right within the rack itself, distributing the massive power via heavy-duty sidecar power shelves.
And because you're packing in dense copper bus bars, massive heat sinks, and hundreds of GPUs, the physical mass of these racks is terrifying. A fully loaded AI rack regularly exceeds a static weight of 5,000 pounds, or nearly 2,300 kilograms. You can't just put that on a standard raised floor. It requires heavily reinforced structural frames, like the Eaton heavy-duty smart rack systems.
The physical dimensions are expanding too. A standard 42-inch depth rack is simply too shallow to house massive HGX server boards. They are expanding to 54-inch depths. The Open Compute Project's Open Rack V3 standard also increases the rack width to 21 inches just to physically fit the massive cabling bundles and allow for improved airflow.
And the building itself has to be reinforced. Concrete floor loading capacities must be upgraded to exceed 800 kilograms per square meter. Otherwise, the massive multi-ton cooling units will literally crack the facility floor in half.
Which brings us to the cooling.
Right.
At densities exceeding 40 kilowatts, traditional forced air cooling explicitly violates the practical limits of thermodynamics. The physics simply do not work. Air lacks the specific heat capacity required to absorb and reject the immense thermal plume generated by that much dense silicon. Air is just too sparse.
You could blow hurricane-force winds through the server hall, and it still wouldn't be enough to keep the chips from melting. Consequently, liquid cooling has transitioned from a niche, experimental high-performance computing technology into an absolute mandate for general AI infrastructure.
Because liquid is dense, it has a vastly higher specific heat capacity than air. AI facilities are deploying 3 primary liquid cooling architectures at scale. First is direct-to-chip liquid cooling, or DLC.
How does that work?
Microchannel cold plates are mounted directly onto the heat-generating CPUs, GPUs, and high-speed switches. The liquid coolant flows through these microscopic channels and captures up to 98% of the generated heat directly at the silicon level before it ever hits the air.
And DLC drastically improves the power usage effectiveness, or PUE, of the facility, right? It cuts overall cooling power cost by up to 40% compared to air cooling, and it can operate with warm water supply temperatures up to 45 degrees Celsius, which eliminates the need for massive power-hungry mechanical chillers on the roof.
The second method is rear door heat exchangers, or RDHX. These are massive, heavy radiators attached directly to the exhaust side of the rack cabinet. The hot air blows out of the servers, immediately hits this liquid-cooled radiator, and is neutralized.
Okay, that makes sense.
A good RDHX system can neutralize up to 120 kilowatts of heat before it ever enters the ambient data center room environment.
And the third method is the most extreme: immersion cooling. You literally submerge the entire server architecture in engineered dielectric fluids. You eliminate the fans entirely. It is highly efficient for loads between 50 and 100 kilowatts, but it requires radical alterations to the facility floor plan.
Because you have to lay the servers down in horizontal tanks rather than stacking them in vertical racks.
Right.
This raises an important question about systemic risk, because regardless of which method you use, the fluid dynamics involved are terrifying. The sources detail that supporting a single 85 kilowatt rack using standard metrics requires a coolant distribution unit, or CDU, capable of pumping 102 liters of fluid per minute through the rack manifolds.
102 liters per minute. That is a massive volume of water. That is essentially a fire hydrant coursing directly over multi-million-dollar electronics.
And a flooded CDU alone can weigh up to 3 tons. You are integrating 3 tons of water directly adjacent to highly sensitive exposed 400-volt DC electrical bus bars.
What happens if it leaks?
If any component within this complex hydraulic system fails, if a manifold leaks or a pump dies, the thermal runaway within a high-density AI rack will critically damage millions of dollars of hardware in a matter of seconds. Redundant flow control and leak containment are absolute, non-negotiable engineering imperatives.
Okay, so let's say you solve it. You reinforce the concrete floors to hold the 5,000-pound racks. You build out the 800-volt DC bus bars. You deploy the 3-ton CDUs and flawlessly pump 102 liters of water a minute to cool the processors without springing a single leak. You have successfully built the physical structure of the monolithic supercomputer.
Success.
But none of this matters, absolutely none of it, if you flip the main breaker on the building and the local utility grid collapses.
And that is exactly where the industry is heading right now, the macro-scale grid crisis.
Because the most intractable limitation facing the global expansion of artificial intelligence is not the manufacturing of silicon, and it's not the advanced plumbing in the data center. It is the generation and transmission of the electricity required to power the system. The aggregate energy demands of these global AI factories represent an unprecedented structural shock to regional power grids.
After a decade of largely flat electricity load growth, a period where the increasing power of computers was largely offset by widespread efficiencies like the adoption of LED lighting and variable frequency drives, the demand for global electricity is experiencing a violent vertical inflection point.
The projections are staggering. Between 2024 and 2030, global data center power consumption is projected by Goldman Sachs to rise by 165% to 175%, driving total data center demand to 92 gigawatts by 2027. And the International Energy Agency estimates that global data center electricity consumption will more than double, reaching approximately 945 terawatt hours by 2030. That is nearly 3% of total global electricity demand, swallowed solely by computing.
And this demand is distinctly segmented into the two computational phases we discussed earlier. You have the training loads, which are highly intensive, centralized processes requiring immense contiguous blocks of power, often hundreds of megawatts for a single facility. But training runs are mathematically finite. They eventually end.
But the inference loads do not end. Inference is continuous. It is decentralized. Every single time a consumer generates an image, every time an enterprise multi-agent system runs a complex workflow, it burns power. Currently, AI tasks account for roughly 5% to 15% of total data center energy, but as inference scales globally, it is expected to surge to up to 50% of all AI energy by 2030.
So developers are rushing to build these gigawatt-scale facilities. A modern hyperscale AI data center can physically be constructed in an accelerated 18 to 24 months if the supply chain aligns. But actually plugging that facility into the high-voltage transmission grid, that process is failing on a systemic level.
It is the interconnection queue bottleneck. The physical building takes 2 years, but navigating the bureaucratic grid studies and utility approvals dictates delays of 7 to 12 years in both the United States and Western Europe.
The public grid was built for slow, predictable municipal growth. It was designed to slowly add a new subdivision here, a small factory there. It was never engineered to handle localized, multi-gigawatt shock loads dropping into a single geographic zone overnight.
Utilities have to perform extensive load flow and thermal-dynamic grid studies before approving a high-voltage interconnection to ensure turning on the data center doesn't black out the surrounding city. In organized markets like PJM and KISO in the US and the primary FLAPD markets in Europe, substation congestion is absolute.
The backlog is almost incomprehensible. Currently, an estimated 3,000 gigawatts of energy projects, which includes both the massive AI data centers and the renewable energy generation meant to power them, are stalled in these global interconnection queues.
3,000 gigawatts stuck in paperwork.
And the withdrawal rate for projects entering the queue has reached nearly 80%. 4 out of 5 projects that apply for power eventually give up and cancel. It signals that the utility interconnection process is no longer a functioning administrative procedure. It is the primary structural driver of project failure globally.
So what does this all mean? I look at this through an analogy. It's like buying the most advanced, expensive supercar in the world, only to realize the line at the local gas station is 10 years long. So what do? You buy your own oil refiner.
Yeah, you build it yourself.
That's exactly what big tech is doing right now.
Yeah.
They cannot wait a decade for the public grid to catch up. So they are using their immense balance sheets to effectively privatize base-load nuclear generation.
The hyperscaler nuclear resurgence is one of the most profound shifts in modern industrial strategy. You have to remember the operational profile of an AI training cluster. It requires strict 24/7/365 uptime. Intermittent drops in power yield devastating utilization penalties on a cluster of interconnected GPUs worth billions of dollars.
Which means relying purely on solar and wind power, while vital for overall grid decarbonization, is structurally incompatible with the continuous, unyielding baseload demands of an AI supercomputer. The sun goes down, the wind stops blowing, and your billion-dollar training run crashes.
To bypass the failing commercial grid queues and secure carbon-free baseload power, companies like Amazon, Alphabet, Microsoft, and Meta are aggressively bypassing traditional utility procurement. They are directly funding the resurgence of the global nuclear power industry.
Look at the plant restarts and colocation agreements. Microsoft has committed to a massive 20-year power purchase agreement with Constellation Energy to literally resurrect Unit 1 of the 3 Mile Island nuclear facility, aiming for 835 megawatts of dedicated baseload power by 2028. Amazon previously acquired a massive data center campus powered directly behind the meter by the Susquehanna nuclear facility in Pennsylvania. They are plugging directly into the reactor, bypassing the public transmission grid entirely.
But the existing nuclear plants aren't enough to satiate the demand, so Google and Amazon are taking it a step further. They are directly financing the development of next-generation reactor technology, specifically small modular reactors, or SMRs.
Google has commissioned a fleet of advanced, fluoride salt-cooled SMRs from Kairos Power, ordering up to 7 reactors to provide 500 megawatts of power by 2030 to 2035. And the critical detail here is that Google is absorbing the massive first-of-a-kind, or FOAP, capital risk through long-term purchase agreements. They are fronting the money to ensure this experimental technology reaches commercial scale.
And Amazon is pursuing a similar multi-module SMR strategy via a partnership with Talon Energy and X Energy. By leveraging their trillion-dollar market caps, hyperscalers are ensuring their AI facilities possess autonomous, stable energy resilience, completely independent of the congested, bureaucratic, and slow-moving public transmission grid. They are literally becoming energy companies.
It is breathtaking scale. But building nuclear reactors, even small modular ones, still takes years. Restarting Three Mile Island takes until 2028. So how do these companies keep their fleets of $40,000 GPUs from sitting idle today while they wait for the concrete to pour and the fuel rods to arrive?
Software.
The answer isn't in hardware, it's in the software orchestration.
Because physical infrastructure construction, semiconductor packaging expansion, and high-voltage grid upgrades all operate on multi-year to decadal timelines, the immediate solution to compute scarcity has to be software. When flagship GPUs cost upwards of $30,000 to $40,000 each, optimizing their utilization rate is a severe economic imperative.
And historically, the software scheduling was terrible. A study of OpenAI's infrastructure revealed that using naive first-in, first-out scheduling paradigms resulted in massive capital inefficiencies. Their highly expensive GPU clusters sat idle up to 43% of the time, despite possessing a massive 6-month backlog of training jobs. That 43% idle rate resulted in $127 million in lost annual utilization value, just burning money while the chips did nothing.
To combat this, hyperscalers are deploying highly advanced multi-level scheduling hierarchies. They use tools like Kubernetes Dynamic Resource Allocation, or DRA, and multi-instance GPU partitioning. This architecture orchestrates workloads dynamically, from massive global resource pools all the way down to partitioning individual memory segments on a single GPU.
Global schedulers distribute jobs across different geographic regions based on capacity, while node schedulers manage sub-GPU sharing for smaller tasks. And when it is optimized, it works brilliantly. By utilizing this highly granular scheduling, operators like Meta have managed to coordinate up to 100,000 GPUs across 12 distinct data centers, achieving a 91% average utilization rate. They squeezed almost double the performance out of the hardware just by organizing the queue better.
But the vanguard of AI infrastructure management involves detaching workloads from static physical locations entirely. It is a concept known as follow-the-sun architecture. It envisions a highly distributed fabric of microdata centers that dynamically migrate live AI compute processes across the globe to chase optimal conditions.
Dynamic workload migration. This is fascinating because it is underpinned by a strict mathematical feasibility domain model. The variables that determine if it is viable to move a massive workload across the planet include the neural network's state checkpoint size, the available wide area network bandwidth, and the duration of the targeted geographic window.
Research indicates that the energetic cost of transmitting massive data sets across continents moving petabytes of data through subsea cables is almost always justified if the destination data center relies on curtailed, zero-carbon surplus energy or offers significantly cheaper off-peak electricity rates.
Beyond purely chasing cheap energy, intelligent global schedulers heavily utilize time zone awareness. They acknowledge that interactive developer usage, the pre-fill and inference workloads where humans are actively prompting the AI peaks during regional business hours and drop sharply at night. So the global schedulers dynamically shift the asynchronous heavy batch training workloads into those underutilized GPUs during the local off hours, seamlessly migrating the compute demand across the globe as the Earth turns.
Furthermore, emerging carbon-aware scheduling algorithms allow organizations to automatically halt non-critical training runs during periods of peak fossil fuel grid reliance. They shift the workloads via live virtual machine migration to data centers in other hemispheres that are currently powered by high-yield wind or solar generation. This software-defined approach fundamentally transforms the AI hardware from a static, localized resource into a fluid, geographically adaptive, and highly efficient compute fabric.
So as we wrap up this massive journey, I want to summarize the true reality of the AI supply chain for you, the listener. The constraint limiting artificial intelligence isn't just one thing. It is not a simple chip shortage.
It is a deeply layered, interconnected gauntlet of physical limitations. It is the photolithographic reticle limit demanding heterogeneous integration. It is the agonizing precision of CoWoS packaging. It is the molecular challenge of hybrid bonding HBM4 vertical memory stacks.
It is the electromechanical latency of spinning hard drives stranding data. It is the signal degradation of copper wiring, forcing a transition to optical computing. It is the specific heat capacity of air failing to cool 100 kilowatt racks, necessitating 3-ton fluid distribution units.
And ultimately, it is the macro-scale failure of the high-voltage electrical grid, forcing hyperscalers to literally restart decommissioned nuclear reactors to guarantee a stable baseload.
Understanding this interconnected physical supply chain is critical, whether you are investing in the sector, building software on top of it, or just using AI in your daily life. It reveals exactly why AI development moves in sudden, violent leaps, followed by structural pauses as the engineers scramble to solve the next physical bottleneck in the chain.
The modern AI data center is no longer a passive repository for server blades. It has evolved into a highly integrated thermodynamic supercomputer constrained by the fundamental limits of physics, manufacturing, and global grid infrastructure.
Which leaves me with the final provocative thought to build on that follow the sun strategy we just discussed. If advanced software can dynamically migrate AI training workloads across the globe, instantly shifting massive computational weight to wherever energy is the cheapest and most abundant, will the massive monolithic supercomputers of the future abandon tech hubs entirely?
It is a profound consideration.
Think about it. As thermodynamic limits dictate that these 1 megawatt racks require extreme liquid cooling and grid queues force the search for isolated power generation, could the most advanced artificial intelligence on Earth soon be trained in the freezing remote Arctic, or in a submerged automated facility next to an isolated geothermal vent at the bottom of the ocean? If the software allows it, these multi